Okay, so homework was bigots, right? And we were supposed to write the four functions for bidgets, but I'm going to keep calling them bigots because it's funny. So the four functions we're creating is zero, is zero, successor, and predecessor. And we talked about the first ones yesterday, last time. Although I guess I assumed that zero would be the container, a list containing a zero, and Brennan pointed out that it's actually the empty list. If you implemented it the other way, that's fine. It's not a huge deal. All right, so let's go ahead and we're going to define zero first. Is that big enough? You see that? So define zero to be a lambda that takes in nothing and produces the empty list. Define is zero like that? Question mark?
I did like a dash and a lowercase c.
Dash like that. Yep. This guy's going to be a lambda that takes in a. Did it tell us what the parameter was, or just bidget?
Yeah, bidget. But you have to switch to advanced student before you try to run it because it will yell at you for the lambda with nothing, taking nothing in for intermediate student.
Oh, really?
Yeah.
So it's going to scream about that?
Mm-hmm.
All right, well, we'll see in a second. And this guy is just going to return null bidget like that. All right, so you're going to say, you're saying it's screaming at me now? Yeah. So it expects there to be at least one variable. So you want to just choose advanced student language. Now you said it's good?
Yeah.
Okay. All right. Now, what we're going to do here, because we assume a n. Now, you could always build this into your function if you want, but what I'm going to go ahead and do is I'm going to say define n to be 16 up there. So now we kind of know what n is. Now, all the other times we use define, we've had lambdas associated with it, right? Define is the way that we create global variables in Scheme. So here's a variable named n, and instead of having it connected with a scary lambda, I just have it equal 16. No problem. All right. So now, next guy we're supposed to create is successor, right? Or predecessor, you can choose. And this guy is going to be the guy that's one greater than the current guy, given the current value of our bidget. So now we got to think about how do we add 1 to a number of base n. So let's open up Keynote here. Oh, so yeah, this is the problem I've been having. Keynote. Well, now, oh, it's just not the top. That's stupid. Okay. All right, so we'll start with the simple case here. So if I have the empty list in, so we'll say n equals 16, and I have the empty list, how do I add 1 to the empty list? Do I have to treat that as a special case? The empty list is a special case. Not gonna. It's not. Doesn't contain mathable stuff. All right. So we got to start off with that guy. So define successor. Did I spell that right? Nailed it. Lambda bidget if null. No bigot. Then return the list 1. That. Else something else. So let's assume I have the list 1. What's the successor to 1? And how do we calculate it? It's 2. Okay, how did you do that? Okay.
I returned 2, so
All right. So let's say we're at a 15 for the car of the list. Now, I don't think they necessarily specify that you needed to convert it to letters there, right? So we just did everything numerically. It's fine. It'll be easier that way. All right. So let's say it's a 15. I want to add 1 to a 15. What should it then become? 15 should become 0, 1. That's 16, correct? All right. So if I have something that looks like this and I want to get the successor, how do I get the successor? You said you wanted to take the car and you want to add 1 to the car. But then how did we determine that that was a overflow or something like that?
If it equals base minus 1.
Well, if the current value equals base minus 1, then what do? We convert that to a 0 and grab the next guy?
Yeah.
All right. And then we keep doing that until what? So we kind of take this a step at a time. I have the list 15. I pull out the 15. I say, is this equal to base minus 1? If it is, I'm going to cons a 0 onto successor of the list. In this case, it would be the empty list, right? The rest, the cooter, as you put it out. Yep. So this is the cooter of the Bidget, which would be the empty list in this case, which this guy would then boil down to the list 1, which would produce for us the list 0, 1. Like that. All right. So we're going to ask the question now. So if I'm dealing with the empty list, I know that I'm done. Otherwise, I know I have at least 1 element in the list. So I'm going to ask the question regarding the car of the list. So if car, well, let's see, if equals car Bidget minus n1. Okay, so if the first element of my Bidget is the same as my base minus 1, then I've reached the maximum size of that. And what will I do? I will cons a 0 onto whatever's returned from successor, passing it the cooter of Bidget. Else, that means the car must not be bigger than it used to be, right? So what am I going to do? I'm going to cons plus 1 car Bidget. So that'll be 1 greater than the first element onto the cooter of Bidget. The rest of it? Make sense? So notice I'm not making another recursive call here because I've done my thing, right? If I had a value that was not going to roll me into the next power over, I add 1 right where I'm at. I'm done. No more recursive calls. Just tack on the rest of your Bidget unchanged. If this says, if I've run out of space in the current bucket, if I can't add any more to it, go ahead and 0 it out and call successor on the rest of the number. Make sense? All right, so this should be successor. So if we test that, if we say successor, and let's go ahead and pass it the 15. There's our 0, 1. Okay. So questions about successor? Not too bad. Now, for those of you who struggled with that one, make sure you're always starting with something like this. This goes all the way back to make sure you understand the problem you're trying to solve before you sit down and try to solve it. If you're still doing this in your homework right now, you're doing it the wrong way. If you're sitting down and you're doing the scheme trial and error thing, where at the end you have this like working program, but you have no clue why it works. How many of you are currently doing that? Too many hands, more hands than should go up. It's like, look, I just kept typing stuff in until it finally like ran. Then I just typed more stuff in until it ran with the right output. Then I tested it on other things and I got some of the wrong outputs then, so I just made everything a special case. Like you have 40 different special cases and hope he doesn't test something outside of that. All right, so predecessor is -1. So if I had the predecessor of 15 here, I'm going to subtract 1 from it, correct? Well, what if I had what's the smallest value we can have in a particular bucket? What's the smallest value a list that has something in it? The smallest value of the car of a list that has something in it? 1. Smallest value I'd ever see is a 1. A 0 doesn't fly. It wouldn't have been there, right? Okay. So if we are taking the successor or the predecessor of the empty list, is that found? I don't think it lets us go to negative numbers, right? So do we want to just say if it's the empty list, return the empty list? Yeah. Because that's going to help us finish a cons at some point, right? All right. So we're going to define predecessor. Did I get it?
Mm-hmm.
Nailed it. Get a star for the day for spelling. Lambda. It reminds me when I was, this is somewhere in elementary school. I was pretty bored in school. I would check out often. And you know how they have like the parent visitation day where your parents sit in the back of the room? So I think my mom showed up one day for it was like a spelling test. And the teacher asked multiple words. You know how the teacher says it out loud and then you write it down? So apparently I didn't move for two or three words in a row. And then the teacher asked if we were ready for the next one. So I wrote down ready. That's the next word I heard. So at the end, we were supposed to have 10 answers. I had 6. You should pay attention in class. All right, so predecessor, lambda bidget, if null bidget, go ahead and just return the empty list. That'll be our special case. Look, I'm not giving you a predecessor to nothing. Here, there you go. Just hand it right back to you. Remind me again, why am I better off returning the empty list here rather than returning bidget, even though I know bidget actually is the empty list? Faster. Why is it faster? Doesn't have to resolve a variable. Good. Now, would it have been wrong to put bidget here? Would our life have continued? Yeah, we would have been. We would have been okay. But if we're really trying to think about the inner workings of our language, especially right now, since we're kind of getting ready to walk right into environments, thinking about how do we actually resolve variables, we're going to realize there's a mechanical aspect to resolving a variable, and that does take time. All right. Otherwise, if I'm in this else, that means I have at least one thing in my my predecessor, or at least one thing in my bidget, rather. Okay, so if it's anything other than a 1, if it's greater than a 1, what am I going to do with it? I want the previous dude, right? Okay, so let's actually handle the simple case first, even though we handled the simple case second before. So I'm going to ask the question. Actually, let's do it. Let's match what we did up above. So we're going to say if equal to car bidget 1. So if I'm looking at a 1 there, then what am I going to do? Am I going to cons anything on? Because that 1 became a 0, which means it falls off, right? So all I'm going to do is call predecessor on the rest. Correct? The real joke would have been just to type in Ray. Get it? Predecessor? Man, that's a tough word. I don't like that word. Killing me. So we're going to call predecessor on the cooter of bidget. Now, realistically, we maybe could have handled it here because we know the nature of our bidgets. But then we could be breaking that idea of recursively specified data. But since we know the nature of our bidgets, if we were dealing with a 1 right now, we know we're going to have room to remove from the next guy, right? So we probably could have kicked over, but we'll let this guy handle it. Actually, that's not necessarily true. Is that true? Could we have 1 in the 1s, 16s? We do have to do something else here because you could have something like 1, 1, 0. So that's 1 in the 1s, 1 in the 16s. If we subtract 1 from the current guy, so if the current guy is a 0, he would drop down, so we would still have the 1 in the next one. So if it's equal to 1, if it's equal to 1, we don't even need to call predecessor. We just return the rest, right? We don't need to call predecessor. The rest of it's correct because we're dumping the guy that we're currently on. No, that's not right either.
Do you want to count to 0 onto the rest of it? Because if you had like a 1, 13.
Yeah, and you would need a 0, but
don't you want to be checking to see if it equals if the car bidget equals a 0? Because then you would have to remove from the next guy if there's a next guy.
so if it's a 1, make it a 0, and we're done. So really, you want to ask if it's a 0, then we're going to.
Then if it was like 0, 13, then it would become
0, 12. No, it would become
15, 12.
15, 12. So if it's a 0, then we want to do this. We would cons. Yeah. Minus n1. So whatever the maximum base is, maximum value you can have there. So we'll cons that guy onto the predecessor of the cooter of bidget and let it do the subtract 1 there. Otherwise, if it's something other than a 0, then we can go ahead and cons minus car bidget 1 onto the cooter of bidget. That the reason we have to do that is if we remove 1 order of magnitude from the if we're in the least significant bidget, I think it's actually correct. If we're in the least significant bidget, which is the car of our list, and we bring that down to a 0, and we still need to subtract 1, then we need to get back to the next guy and get 1 off there, but now we need to kick this up to the maximum value because we're rolling it back. So that's why we're consing on this value minus 1. All right, so a good test for this one would be predecessor, maybe give it the list maybe 0, 1, which is the number 16. And if we want that to go to 15, then it's going to become just the list 15. We actually still have the 0 on there. That's not incorrect, but I don't necessarily like that. I think the way to test that is if it's the empty list or it's a list containing one element and that element is a 0. This isn't inaccurate. This is a correct representation of a number, but if we really wanted to peel off this last 0 because it's not necessary, it's think about a binary number. Since this is least significant to most significant, if we reverse it, you can put as many zeros in front of a binary number as you want, and it doesn't change the value of it. So that's kind of what we're dealing with here. So one thing we could do is we could say if it's null or the length is 1 and the car digit is 0. If either of those things are true. So if I'm dealing with the empty list or I'm dealing with the one list whose length is only 1 and whose car is 0, well, this is going to handle that 0 there.
You can choose to check if the car is 1. Then if it's a 1 list, it's gonna
Then we handle this as a special case. Yeah, so if the car of it is 1, we know we're going to be ticking it down to 0, but it's a 1 list with a car of 1. Therefore, we know that's going to be a list that would only have a 0 in it. Now we'll just make it the empty list. So maybe a little bit cleaner, although this is substantially scarier. So I'm not sure if there's really an advantage to that or not. All right, questions about that? So these are our 4 functions. Mm, 470. Okay, now I think we're on to environments now. Let's kick over to this. I mean, this next question here, 2.3, define a representation of all the integers, negative and non-integer, as diff trees, where a diff tree is a list defined by the grammar. We could have a diff tree of a difference of 1 or a diff tree with 2 diff trees in it. So this is just another representation of numbers, but this one brings in negative numbers. So kind of belaboring the point. All right, so let's look at the environment interface. All right, so they're defining what an environment is, and really we have 3 different functions that they're talking about here. We have something that we're calling the empty environment. So the empty environment is an environment that is an empty list for us. It's a list containing no name value pairs. For us right now, when we think about a variable environment, that's a synonym for name value pairs. Okay? A lot of programming languages these days have built-in data structures called dictionaries that allow us to pull off this whole name value pair type thing. Now, typically a dictionary doesn't allow you to store what are called closures. Doesn't allow us to store lambda expressions. It allows us to store string-based names with a variable type. Now we could store like linked lists and stuff as our value if it's built into the language. But if we need a list of name value pairs, if we need a way of representing JSON type data, we might use a dictionary. So we would have our own implementation here. So we would have an empty environment. So if we want to think about an abstraction for that, define empty env to be a lambda that takes no parameters and returns the empty list. That's an environment containing nothing, 0 name value pairs. All right, now we're going to skip the apply here for a second, because this next guy, apply env, takes in a variable, and it's a function and a variable, and it applies that variable to that function. But this essentially is our lookup. That's how you find out what the value of a variable name is. If I define a as being equal to 5 and I want to get the 5 out again, I need to apply the environment, giving it the a, and say go and find a in this environment. The most local definition of a. So remember before we've referenced in other classes that all variables resolve to their most local definition. So we're going to check in the most local scopes first. All right, so now we have this idea of an extend env, where how do we extend env takes 3 parameters. First parameter is the variable name, second parameter is the value, and the third parameter is the environment we're extending. Okay, so define extend env to be a lambda that takes in a var name, a var val, and an environment. And what are we going to do? We're going to tack on this, it's a scope, right? So right now each of our scopes only contains a single element, since we've in this particular definition, we have, when we extend an environment, we're only extending with a single variable value pair. So not real useful scopes, but scopes nonetheless, right? All right, so what are we going to do? We're going to represent our environment. So this guy is going to give us a list containing, well, actually we can do this. Let's cons the list containing var name and var val. And we might end up with a slightly different implementation the book uses, but this is going to give us this idea of a variable environment. I don't know what they actually end up implementing in this, but this will be good enough for in-class example. So we're going to cons a new list made up of our name value pair onto the existing environment. Make sense? Okay. So that's how we extend an environment. So now we could create something like a extend env. Actually, let's do this real quick. Let's do define env to be a empty env. And then we could say extend env a5 env. If we want to extend that further, we can say extend env. We do not need those parentheses. B7 extend env a5 env. That's a symbol. That's a symbol. List. All right, so here's our most local environment that has B and 7 in it. And here's the next name value pair after that. So we have a list of 2 lists. right? We seen that before? Haven't we had some problems we've solved in class that were effectively lists of two lists that we manipulated? Okay. So as an example, we can define E to be this giant environment where we extend E and V with D6, then Y8, then X7, then Y14 onto the empty environment. Okay, and that's going to give us a whole bunch of variables that we have access to. Let's see, what is this guy? Okay, we might have you do that one, actually. That's an interesting one. So let's get down here to, so again, this is just a different way of explaining that environment thing. Makes pretty good sense. Right now it's a list of two lists. Later on, it might be nice to have more than one variable inside of a single scope, but that's not what we have quite yet. So now we're starting to walk into this idea of an interpreter. Okay, we go way back to this idea of, remember we said there's two kinds of programming languages. We have compiled languages and we have interpreted languages. Okay, what's the difference between a compiled language and an interpreted language? Well, compiled languages, how do they work? We put something through a compiler. What does a compiler do? Oh, come on, people. Translates between what?
The human code versus machine code.
Okay, ish. So it translates from a high-level language to a low-level language. That's what the compiler does. All right. So compiled languages, we send it through the compiler before runtime, right? And so then we have all this low-level code that then during runtime runs natively on the CPU. Interpreted languages, like we're going to write here, and like how Scheme works, are languages where we are doing that semantic processing of the logic in real time while it's running. Now, that probably means that interpreted languages are typically slower languages, right? We weren't able to, because now kind of in real time, usually the example I use when I first teach that concept is something with somebody's giving a speech and you have an interpreter who's having to, in real time, listen to somebody give the speech and convert it into a different language. Speech is given in English, you're having to convert it into German. There's a little delay there, right? That's what's really happening with our interpreters. So when we write our own language here, it's going to be an interpreted language. So when we write our code, we effectively are kind of walking through it line by line or function by function, and that creates a new state of our, whether it's scopes or where we are in applying a function, whatever it is. All right, so here's the recipe for this interpreter. So we're going to look at something, we're going to decide what kind of thing it is, and then we're going to extract the components of it and do the right thing with them. So for instance, if I look at the car of a list and the car of the list says if, that's going to give me some information about what I expect to also be there, right? I expect there to probably be a Boolean expression in the catter, and I expect there to be a whatever the true expression is, the stuff I should do if that Boolean expression boils down to true in the car of the cooter, and I expect the false expression to be in the car of the cooter. Make sense? But because I read that car, because I saw it was like an if, that gave me information about what I should do next, assuming it was legal code. That makes sense? So that's what they're saying here. Interpreters are going to read something, decide what to expect from there, then extract the pieces and operate on it.
The difference is the compiler does all that in advance before it executes.
Sure. Yep. Okay. Now, one thing that they've kind of done here in their implementation is instead of So they created it was in a list, I think, wasn't it? Yeah. So what they did for their empty environment is they created a list that had the symbol empty env in it. Empty. Nope, still wrong. Empty.
What I found on the web for empty.
Killing me. Nailed it. First try. All right, so empty env, and then they call this guy, when we con something on, I assume they're going to just put extend env on that. Yeah, list extend env var val. And they're actually wrapping it. So in their implementation of this, the new scope contains the old scope. Instead of it being a list of two lists, it's a list of environments, where environments are living inside of each other. So that's okay. Kind of like the thing we've done the last couple classes with the different ways of representing numbers, different ways of representing environments. At the end of the day, we just need to be able to extract stuff from however we write it. We need to be able to extract from it. All right, so here's our extend env. Then they have this thing called apply env. All right, so if we kind of walk through this a little bit, apply env is going to take an environment and then the variable we're searching for in that environment. Okay, now we have this new thing called a cond. Now, have we seen it before in the book yet? Anything you've looked at in the book? So a cond is like a switch statement, which I usually don't teach in the programming classes because I'm not big fans of them. But when you have a whole bunch of nested ifs, and we're starting to see in our patterns that we have an if this, then, if this, then, if this, then, we start having ifs inside of ifs inside of ifs, a cond might make sense for us. So the syntax for a cond is if the car of our environment is the empty environment. So that's kind of like the null list thing, right? Similar pattern, just now we're dealing with an environment. So the first question we're asking is if we're dealing with the empty environment, then this is kind of a function. Report no binding found. This guy right down here where this is essentials of programming languages error, something built into it. We're just spitting out that we couldn't find it. So it'd be perfectly acceptable for us to just return false. We don't need to have huge error message outputs or something like that for us to understand the concepts here. All right, so look, if I am searching for the current environment for the variable that we're looking for and I'm looking at the empty environment, I have run out of runway. Okay, no value was found. If the car of the environment is an extend env. Okay? If it's an extend env, now we have a new thing. This is something we've been waiting for. And we have a way of creating a local environment. So if I'm looking at an extend env, it's going to be something that has a name value pair in it and then potentially some other things, then I'm going to create a local environment here. So I'm going to let some variables equal some stuff. So a let takes in a list of name value pairs. So here is that list that it's taking in. So I'm going to have the saved var as being the catter of the environment. That is the thing that's the first element of the list after extend env, after the symbol extend env. So this will get me the variable name. This will get me the value of that variable. And this will get me the next environment that this extend env is wrapping. All right, so even though it looks a little bit scary, all we're doing is we're creating three little local variables here inside of this let. Okay, three little local variables that then give us access down here. So all this stuff right here is happening within this mini environment set up by this let. Okay, So, well, we're still living in this area right here. Everything I have highlighted right there is governed by all the variables we had before this. So it has access to env, it has access to search var, but now it also has access to these three new, let's call them temporary variables. So we have saved var, saved val, and saved env. Then we're asking the question inside. If the val that we're searching for, this guy up here, which is one scope up, is equal to the var that we're currently looking at. Now, we didn't need to create a let to pull this off. Let just made our logic down here a little bit more convenient and made the catter stuff, this kind of the scary extraction pieces up here, a little bit cleaner. It also fit with this third rule of our interpreter recipe: extract the components. So that's the pattern we did here. We said, okay, I'm looking at an extended env. What do I do with extended envs? I start by extracting the variable that's defined in there, the value of that variable, and the environment that we're extending, and then I ask some questions about that. So I'm asking, is the variable that we just extracted equal to the search variable that we're looking for? If it is, here's the value of that variable. I've resolved that variable. Make sense? This is variable resolution. Otherwise, I'm going to apply env, so I'm going to call this function recursively, passing it the saved environment, passing it the search var. The saved environment here is not the environment that was passed in. Instead, it's the environment that this extend env extended. So it's the encapsulated environment inside of there. Make some sense? So I'll call apply env on that. Now, one thing, and this isn't going to make tons and tons and tons of sense for us right now until we see the other versions of lets. We have a let star and we have a let rec. And all they've introduced here is let. This is a temporary environment. It does not survive recursion. And that's okay. We don't need it to survive recursion. It gave us access to some local variables. And really, this is probably overkill for a let, since we're asking such a small question here. You know, we took, 6 lines to do something we probably could have done in 4 without a let. But it at least kind of gives us access to that. I've given myself 3 name value pairs, and then I'm going to use those to call apply env. It's maybe a little bit cleaner than if you start having all these catters and CADDRs and all that stuff. That starts becoming difficult to follow. Doesn't read real well. All right. So if it's the guy I was looking for, go ahead and return it. Otherwise, call apply env with the variable I'm still looking for with the environment that lived inside of the current scope, inside of the extend env. Otherwise, if I'm still kicking here, this is the else to this con, that means whatever they passed me just wasn't even an environment. Just you gave me something that's just broken. I can't handle that. And so this is the error message thing for that. Okay. Let's see what we should do for homework. Let's do 2.4. I like that one. And then maybe something with environments. Yeah, I really like that one. I don't like that one. .9. I think that's a good one. So let's do 2.4 and 2.9 for our homework. Sound good? All right, I'll see everybody on Friday.